Okay, so we had, well, the log base a of x to the r is r times log base a of x. We had that the log of the product of two things, we can break that up as the sum of the logs. And we had that the log of the quotient of two things, we can rewrite if we wanted to break them up as the difference of the logs. And we played with a bunch of really fun little examples. So what I want to do now is solve a bunch of different sort of functions or equations involving either exponentials or logs. Okay. So what we're going to do, I've got 1, 2, 3, 4, 5, 6 examples, maybe. We might not need to go through all 6 of them, but I certainly want to do enough examples that you all feel very comfortable with the process. Okay. Well, this kind of goes back to a question in I got to do this one. Ready? This is kind of a 4.3 kind of example as well, but it's really worth doing. Okay. What if I want to solve, and this first one is 8 times 1.08 to the x is equal to 20 times 1.11 to the x. Ew. Right? So we want to find the value of x that gives us equality here. Okay, this looks yuck. I think you'd agree. So what I will say is as follows. In algebra, thus far, we have learned that when we're solving for x, what we want to do is get all the terms with x on the same side of the equation. Okay, isn't that kind of a tactic that we've used thus far in algebra in our life? If you want to solve for x, you get all your terms with x on one side, everything else on the other. So what I'm going to do is I'm going to bring all my terms with x over to the right side. It does not matter which side, does not matter. How do I bring this term over to this side? You divide both sides by it. Do you agree then? On my left, I have an 8, and on my right, I have just a total mess. Okay, now I want to move this 20 over. How do I do that? Divide both sides by 20. So I have 8 over 20 is 1.11 to the x over 1.08 to the x. Questions this far? All right. Well, 8 over 20 is 0.4. Let's at least make one side look dealable. Questions this far? Okay. All right. We're going to use a property of exponents in reverse. Do you remember the property of exponents that says when you have a quotient raised to a power, you can bring your exponent into your numerator and denominator? We're going to take this and go this way. In other words, I have this to the x divided by this to the x. Can't I put that as 1.11 over 1.08 to the x? Questions how I got from here to here? Okay. Well, we could either leave it like this for right now, or we could divide it and get some decimal approximation. I'm just going to leave it because I am. Okay. I want to solve for X. When your exponent is unknown, how do you solve for it? You take the log of both sides, right? Isn't that the way to get our exponent out of there? Doesn't matter whether we do the natural log or the log log. Who do you want to do? Natural log. So I have the natural log of 0.4 is the natural log of 1.11 over 1.08 to the power of X. What's the really great thing about having taken the log? What can I do with this X? Down in front. And now I want to get X all by its lonesome. The problem is I'm multiplying by this yucky looking thing. How do you get rid of what you multiply by? Divide. Oh my gosh, I love your enthusiasm, even if it is forced. But maybe it's. So my final answer is the log of 0.4 divided by the natural log of 1.11 over 1.08. This is the exact answer. Now, probably what we would be doing is getting a decimal approximation. Do you want to see me plug it in my calculator? Or are you guys cool plugging this in your calculators? I'm happy to show you if you need it. If you don't need it, I don't want to bore you.
How does it go to the calculator?
You ready?
Yeah, we're gonna. Sure.
Okay. See my calculator? I do too now that I put my glasses on. So I hit natural log of 0.4. I'm going to close my parenthesis. Divided by the natural log. I'm going to do 1.11 divided by 1.08 and close that parenthesis. And shazam, we get negative 33.44. What a cute little answer. Y'all with me here? You ready? What if I wanted to solve this one? Log base 3 of 2x plus 4 equals 2. When things are written as logs, we're pretty clueless, especially if it's not log base 10 or log base e. So whenever you're asked to solve a log equation, you want to do the mantra to change it to equivalent exponential form. So let's do that. How do I write this in equivalent exponential form? 3 to the power of 2 is equal to what I'm taking the log of. Can I solve this? One hopes. What's 3 squared? 9 equals 2x plus 4. What's my first step? Subtract 4. So I'm solving 2x equals 5. Divide both sides by 2. And I get x to be 5/2. Isn't that a little cute little thing? What if I want you to solve log x to the 5th equals 3? Okay, what do we do here? Yes, we change it to equivalent exponential form. I don't have a base written here. What do I do? 10, good. So in equivalent exponential form, isn't this 10 raised to the third power equals x to the fifth? What's 10 cubed? 1,000. But I don't want x to the fifth, I want x. How do I get rid of raising something to the fifth power? Raise both sides to the 1/5 power. And if you compute 1,000 raised to the 1/5 power, you're gonna get about 3.981. You okay with me this far? Eric, you good? Cool. Okay. Now we can make use of some things we did on Monday. What if I want to solve this? Log of x plus 5 minus the log of x plus 2 equals 2. Well, we know when we have logs and we want to solve things that we change it to equivalent exponential form. Thing is, we got 2 logs. So using those properties that we talked about yesterday or Monday, last time, can we write this as just 1 log? We can. When you have the log of something minus the log of something else, how do you write that as a single log? What do I, good, I divide. Do you hear them clap? No, it was for Ross. He told me what to do. He's the one who told us what to do. No one ever claps in a math class, except for perhaps when I say, this is the last day of class, right? I wish when I was a grad student and I was in my math classes, I was so excited by the math. I would want to stand up on my desk and cheer, but anyway. All right, change it to equivalent exponential form. What does it look like then? What's my base? 10 to the power of 2 equals x plus 5 over x plus 2. Well, I think you'll grant me that 10 squared is 100. Now I look at this and I'm like, ew, I got a fraction here. I got a denominator with a variable. Can I get rid of my denominator here? Yes, we know how to get rid of denominators in math. We multiply. So do you agree if I multiply both sides by x plus 2? They'll cancel out right here and I'm left with x plus 5. And on my left, I have 100 times the quantity x plus 2. What's so funny? So let's get rid of our parentheses here. Can I distribute? Yeah. 100x plus 200 is x plus 5. Now what do we do? Good, let's get all of our terms with x on one side and our numbers on the other. So I'll subtract x. So I have 99x plus 200 is equal to 5. Now what? Subtract 200, so I get 99x is negative 195. And now divide both sides by 99. Not the prettiest answer, but I would say that's a relatively cute little thing. Ready? Or do you need me to leave this here a bit? Yeah, take your time. I'm just excited. Cool. All right. Okay, let's do this one. I have two more to do. This one looks a little bit like the last one, and then the next one doesn't. What if I have log x plus 15 minus log x minus log 15 equals 0? I love your facial expression. It's good to have emotions towards what you're doing, even if they're negative ones. You ready? Okay. What we want to do is write this as a single log. Okay. Okay. We could do it to one at a time. So let's just deal with the first bit. Okay. I'm going to do that right down here. Do you agree? I could say that's log of x plus 15 over x. Thanks. You with me this far? So now I have the difference of two logs. I just combined these two. So what do? I say it's the log x plus 15 over x. And since I'm subtracting here, don't I divide by 15? Well, isn't this x plus 15 over x divided by 15? I just rewrote that. And when you divide by a fraction, you multiply by the reciprocal. So I claim my left side becomes x plus 15 in my numerator, 15x in my denominator. Questions this far? What am I going to do now? Yes. You don't have to sing the whole jingle. Okay, what's my base? 10 to the power of 0 is x plus 15 divided by 15x. What's anything raised to the 0 power? 1. What can I do now? Multiply both sides by 15x. So I have 15x is equal to x plus 15. Next, subtract x. So I have 14x is equal to 15. So isn't x equal to 15/14? You with me? Okay, one last one for this section. What if I have the log of 2x minus 7 is equal to the log of x plus the log of, let me do 2x plus 7, 4. We're looking okay on the left side, right? I mean, it looks like kind of a mess, but we're just looking at the log of 2x plus 7. Can I rewrite this as one log? How can I write that as one log? The log of what? 4x, right? When you're adding two logs, you multiply what you're taking the log of. Well, notice on both sides, I have log base 10. If you have the log equal to a log, isn't what you're taking the log of going to be the same? So I'm saying, hey, if the log of m is equal to the log of n, then these two things must be the same. So from there, don't I have 2x plus 7 equals 4x? And we can totally solve this. Subtract 2x from both sides. So we get 7/2. How's this? Okay. So what I want to do, give me 1 second here. No, if you're in different bases, I mean, you could use a change of base formula, but you won't need to go there. So what I want to do for a second, oh, cool. Wrong class it's opened up to. But here's M121. Let me share my screen with my Zoom friends. Okay. So 4.4 is going to be due a week from today. I want to point out that when we're done with 4.6, we're going to have our next test. Okay, we have 4.5 and 4.6 left to go. Okay. Remember, we have our next test when we're done with chapter 4, and then it's on 2 chapters. What I want to do just very quickly is show you some of the homework here. Okay, just so that like nothing comes as a surprise. So in this section, you just want to write this as a single log. Okay. So combine them, right? You can, because they have the same base. And when you add 2 logs, what do you do to what you're taking the log of? Multiply. Beautiful. Here you want to do a similar thing. Write it as a single log. They tell you how to write this, you know, using the base this way, or you can also use that function tab that they have. Okay. This one, you're going to want to break it up. In other words, to the sum and difference of logs, and then bring your exponents in front. They just want to know what your exponents are. Here, you're doing the same thing. Oh, look at question 5. Oh, wow, I used my exact numbers. Hopefully you won't have, or no, I didn't. Maybe I did. No, I didn't. Okay, we solved one of these at the beginning of class. How do you deal with these? you change them to equivalent exponential form and solve them. So that's what you're going to do for question 6. That's what you're going to do for question 7. Here you can combine those. And here, notice it's like the last one we did, log of both sides. You okay? Cool. All right, so what my plan is to next cover section 4.5, and then we'll spend some time on section 4.6. So the thing is, this Friday, we're going to do 4.5. I don't know how far we're going to get. So here's today, 4.4. I'll just start 4.5. Friday, we'll do 4.5. Next week, so that's the 7th, the 9th, and the 11th. We have class on Monday. We'll do hopefully 4.6 started on Monday. Tuesday, as you all know, is a day off. Doesn't affect this class. We don't ever meet on Tuesdays. Wednesday, we're going to be doing 4.6. Thursday is a regular day, but it's irrelevant to us because we don't meet that day. Friday is another day off. Okay. Election Day, Veterans Day. My hope is to get through all of 4.6 in those days so that on Monday, the 14th, we can take our second test. If we need to push it to Wednesday, the 16th, we can, but let's see how it works. Just so you're aware that not next week, but the week after, we're going to have a test. Okay.
Are you,
Oh, sure. I just wrote myself a note. Okay. So if I don't write myself notes, I'm done for. If you came into my office, you'd see that I have notes everywhere. Okay. What we're going to do in section 4.5 is we're just going to look at our log functions a little bit deeper. We're going to look at the graphs of our logs. We've played with them a lot. What we want to do now is just get a better feel. Okay. And pretty much everything that I am going to be doing here in this section is going to be using the fact that our logs are inverses of our exponentials. And so we're going to be using those properties like crazy. Okay. All right. Now, I promise you there's not too much that you're going to be responsible for in this section. But for me, when I talk about functions, I like to have a feel for what's going on with them. Okay. So the first thing that I want to do is give you a reminder. I want to give you a reminder that when you have inverse functions, F inverse, this is the domain of F. And this is the range of F, going back to some verbiage we used at the beginning of the semester. But notice our outputs of our function become our inputs of our inverse. So this is precisely the domain of the inverse. And this is precisely the range of the inverse. We saw that with a function and its inverse, if xy is an ordered pair with my function, we bebop ordered pairs. Yx is the corresponding ordered pair for my inverse, right? Like if my function takes 1 to 2, then my inverse is going to take 2 back to 1. Okay. Now, the inverses that we're dealing with now look a little bit more complicated. These two functions are inverses of each other. Okay. And just like with exponential functions, whether you graph 2 to the x or 3 to the x, they're slightly different, but the general shape and the pattern is the same. So what I'm going to do is say, okay, you know, it's hard to have a feel for logs, but we do already have a feel for exponentials. So let's take these ideas and apply them, okay, to get a feel for what we have going. In other words, what I'm going to do is take, say, 2 to the x and log base 2 of x. These are inverses of each other. Okay. Let's just take some values here and plug it in. If I take x equals 0, what's 2 to the 0 power? 1. If I plug in x equals 1, what comes out? 2. If I plug in x equals 2, what is 2 squared? 4. And we could keep going. Let's plug in -1 now. What is 2 to the negative first power? Good, 1/2. Right? 2 to the -1 is 1 over 2 to the first. What if I plug in -2? What's 2 to the negative second power? 1 over 4. Right? Because it's 1 over 2 squared. So these are my ordered pairs, right? So for this exponential function, do you agree what I've established are 5 ordered pairs? 0, 1, 1, 2, 2, 4, -1, 1/2, -2, 1/4. So we know the corresponding ordered pairs for our log function. What's the corresponding ordered pair for my log function for this guy? 1, 0. How about this one? 2, 1. How about this one? 4, 2. How about this one? Thank you. 1/2 -1. And finally, how about 1/4 -2? Okay. Let's also do one more thing with our exponentials. Let's talk about our domain, our range, our y-intercept, and our x-intercept. Anyone remember what the domain of exponential functions is? Yep, all reals. -infinity to infinity. Anyone remember what the range is? 0 to infinity. Good job. What's my y-intercept? It's right up here. Isn't it the ordered pair 0, 1? And remember, there is no x-intercept. We have a horizontal asymptote at 0. All right, well, from here and from what we know about our inverses, we know the domain of our function is the same as the range of the inverse. And the range of my function is the domain of my inverse. So given that, can we talk about the domain and range of our log function? Well, remember, the domain becomes the range. So isn't the range now all reals? And what is my domain? 0 to infinity. Good job. Notice if my exponential function always goes through 0, 1, at least in this plain form here, the corresponding ordered pair is 1, 0. In other words, what do we have? If 1, 0 is always on there, don't we have an x-intercept at 1, 0? I just flipped these ordered pairs. By definition, your x-intercept is your value of x when y is 0. And if this never touches or crosses our x-axis, the same thing is going to happen over here. It's not going to touch or cross your y-axis. Right? Everything bebops. X becomes y and y becomes x. Now, this is a heck of a lot of information. And what we're going to do now is we're going to draw a really pretty picture. Okay. Well, for my exponential, it's 0, 1, 1, 2, 2, 4, negative 1, 1/2, etc. Do you agree that this is my exponential function? I'm now going to plot the ordered pairs for my log. I'm at 1, 0. I'm at the ordered pair 2, 1. I'm at the ordered pair, 2, 1, sorry. I'm at the ordered pair 4, 2. Then I have the ordered pair 1/2. I'm down at negative 1. At 1/4, I'm down at negative 2. This is what your log function looks like. One thing that we see with our inverse functions is they are reflections about the line y equals x. Isn't this a mirror image of that? So in general, what we have is the following, and I've got one more thing to introduce to you for these log functions. In general, log base a of x. Our domain, notice you can only take the log of positive numbers, is from 0 to infinity. Our range, our outputs, are all reals. They go from negative infinity to positive infinity. I'm just rewriting what I have up there. We always have that x-intercept of 1, 0. Notice we don't have a y-intercept. This never touches or crosses our y-axis. But something significant happens there. Do you agree, as my x values are getting closer and closer and closer to 0, my function's shooting down to negative infinity? You guys, look outside, it's snowing. So my function is shooting down to negative infinity. This is called a vertical asymptote. Okay. I claim we have what is called a vertical asymptote here at x equals 0, right? This is my line x equals 0. In general, and we're going to get way into these in chapter 3, you have a vertical asymptote at x equals some value if, as x gets closer to that value, your function values either shoot up to positive infinity or shoot down to negative infinity. Oh, yeah, we'll be shifting it, but this is our general. Oh. Sorry. That's what you meant. You can never plug a negative number into a log function, but you can shift your graph up, down, left, right. Okay. Then you'd have to have like log of, say, x plus 7, and then you'd be over here. And we'll get there. We'll get there. So one key thing that is very important for anybody who's going on and doing a calculus class, you can't take the log of a negative number. That's like a really big no-no. Now we can have shifts, you know, so for example, what if I have f of x is, say, log base a of x? Okay. What if I wanted us to find f of, say, x minus 3? Doesn't that mean that everywhere where we see an x in our function f, we're going to plug in x minus 3? When you subtract 3 within, what does that do to your graph? It shifts it right 3 units. So if our general log is right here, 1, 2, 3, here's our shifted graph. Now, notice the domain of our log x has got to be greater than 0. In other words, look right here. Doesn't that mean for my domain of this new guy, I need x minus 3 to be greater than 0? Because the total of what I plug into my log has got to be positive. In other words, I can only plug in values greater than 3. Notice in this new one, I have a new x-intercept. What is that? 4. And notice my vertical asymptote is precisely that cutoff value, x equals 3. So from there, what I want to say is if you have y equals log base a, say of x minus k, the domain is that x minus k has got to be greater than 0, i.e. x is greater than k. And I claim that value of k is your vertical asymptote. Do you want to do one more example? Thanks. We only have a few minutes, but I think we got it. So what if I want you to find the domain and vertical asymptote of this function? Log of x plus 2. Don't I need whatever I'm taking the log of to be greater than 0? In other words, don't I need x plus 2 to be greater than 0? So what does x have to be greater than? -2. And what's my vertical asymptote? X equals -2. Now check this out. If this is my log function, when you add 2 within, what are we doing? Shifting it left 2. So 1, 2. There we go. Isn't that cool? Cool. All right, we'll pick this up on Friday. Have a great day. And by the way, it stopped snowing, so you can smile. I know, short-lived excitement for all of us. All right, see y'all. Thank you, Kiki.